So I forgot to bring my markers to class for multivariable calculus. And so I wasn't able to record the first lecture. And if we're going to do this recording in the future, I want to make sure we have the first lecture so there's context. So I'm going to try to recreate as best I can. Hopefully this won't happen again. And we're going to start our lectures with sort of a thought for the day, or maybe a strategy, something that will help us prepare, something that will help us learn. And so the first one is a quote, maybe a little bit on the heavy side, but it's a nice idea. And it says, "The greatest obstacle to discovery is not ignorance. It is the illusion of knowledge." All right, now a few notes. First off, when we talk about discovery, for us, that includes learning. So you can certainly say, okay, what's our greatest obstacle to learning? Well, it's not that you don't know things. We can help with that. It's that you think you know things. It's this illusion. And so I want to talk about what this illusion can mean, and so that you're aware of it. And if you're aware of it, you can say, I can work to make things better. And I think it really goes into two big categories. So where do we have an illusion of knowledge? Well, one very common, very frequent place where people think they know things, but not as well as they should, is background. So you're coming into this course, you say, okay, I know things, and I've learned things. I know algebra, I know calculus, and I'm great, I'm good to go. Well, the problem is sometimes you do know them, but you don't have them practiced well, so they're not quite at your fingertips. The more dangerous thing is sometimes you learn things the wrong way. And so we have to do some deprogramming, if you will. We have to help you say, this was not the right way to think about things. This is not the right way to do things. Here's the right way. Let's get to that proper setting. And so be ready to say, okay, maybe something I thought I knew, I didn't really know. And so given that, I can do better. I can do better. Okay, so once we fix our background, the other thing that can happen, the illusion of knowledge, is that we watch our instructors, and they make things look easy. In other words, they're doing a problem. Every step is clear. Their chalk or their pen, everything flows. Life is good, and you're like, this calculus stuff, my gosh, it's the bee's knees. I'm never going to have a problem. Life is good. Life is wonderful. But here's the thing. When you see people do things that look effortless, there was a lot of effort that went into that. And that goes for all things. Musicians, athletes, just anybody who's put a lot of time in, they'll make things look easy, but it's not. So don't fall into this illusion that says, when the instructor did it, it was pretty obvious. So when I'll do it, it'll be pretty obvious too. Because you'll get to that time, a quiz, exam, and you're like, wait, what? What happened here? Things aren't so obvious. Okay, so put in the work. Put in the work. And if you put in the work, fix your background as needed. Make sure you say, look, I'm not going to depend on thinking that things are easy. I'm actually going to do it. You're going to be in great shape. All right, good. Well, there's our thought for the day. So now we're going to move on and start talking about what is this course? Well, it's multivariable calculus. And if you think about the journey that you've had to get here, we've gone through 3 stages. So we have our Calc 1 course. And in Calc 1, what did we learn about? Well, we learned about differentiation, and we learned about integration. All right, so we can differentiate and we can integrate. And then in Calc 2, well, we went there. What did we learn about? Well, we went into, I would say, I don't want to call it advanced integration, lots of integration stuff. Applications and ways to manipulate. And spoiler alert, most integration that you can actually, the integration happens here. Most of the Calc 2 integration is like, well, there's only 10 things we can integrate. So let's make it look like those 10 things. So most of the Calc 2 is algebra and trigonometry. It's like, how do I get to those 10 things? Of course, the fun thing is we have sequences and series. Good times, good times. And now we're in Calc 3. Well, what is Calc 3 going to be about? Well, we're going to basically say, let's take the ideas and let's build off of them. And we're going to go through, and there's going to be 3 things. Now, Calc 3, this is multivariable calculus. And essentially, we're going to add an extra dimension. In other words, if we think about what we've been doing, oftentimes we've been doing things in 2 dimensions. Y is a function of x. But now we're going to be in 3 dimensions. So instead of having something like, as I was saying, we have, I have a curve here. Now we have something in 3-dimensional space. Okay, so maybe it's not a curve, but maybe it's some sort of lumpy surface. And we say, okay, well, great. How do we understand these things? And, all right, so generally speaking, we have that Calc 3 is going to be multivariable, and it's going to build off of 3 things. We're going to do geometry, and then we're going to talk about differentiation, and we're going to talk about integration in this higher dimensional setting. Now, I want to talk about some of your challenges that lie ahead. And so for context, what were the challenges in the past? So for Calc 1, well, the big challenge for Calc 1 is understanding. And it takes a while to figure out what's going on. And once you understand things, life is not so bad. But again, it's not easy. Calc 2, okay, this one, it's algebra and trig. They really, really lean in to those ideas. And in Calc 3, what's our challenge? Is geometrical understanding. So each one of the courses offers a different challenge. Now, I have some good news, and or maybe some sad news, depending on your perspective. You might say, well, okay, how bad is it going to be compared to these classes? Well, the punchline is that Calc 1 is really the ideas we're going to build off of. We're kind of going to skip Calc 2. We'll mention a few things here and there which tie back to Calc 2, but very minimally. So in essence, we're essentially taking the Calc 1 tools and we're just saying, okay, how does it apply in higher dimensions? And spoiler alert, it turns out that when we talk about multivariable calculus, it's essentially single variable calculus. We just have to do things multiple times. So that's some good news for us. All right, so again, we're going to talk about geometry first. That's the first third of the course. Get into differentiation, there's the middle of the course, and get into integration. That's the end of the course. All right, so if we're talking geometry, let's get into that. So we need to understand, what is our space? So we're going to spend essentially the whole time in 3-dimensional space. And we have some good news about 3-dimensional space. We're pretty used to 3-dimensional space. Some of our best friends live in 3-dimensional space. Well, actually, we live in 3-dimensional space. And so we can think of it as I should have come up with a better word. I was going to say space, but that seems kind of silly now. So let's think about how we can describe it. Now, describing things is the first step in being able to do mathematics with things. And so we say, okay, well, how do we go about it? Well, we can say there's a point that we'll fix, and that's the origin. So the origin is the point 0, 0, 0. So that's our fixed point. And essentially we say, okay, we go into this 3-dimensional space, and we say, let's just pick a point, and there's our origin. The other thing we're going to do is we're going to pick 3 mutually perpendicular directions to describe things. Now, we'll mark them here and say we have the x direction, the y direction, and the z, or for our UK followers, z direction. X, y, z. And when I say they're mutually perpendicular, that just says that these here are all right angles. Okay. Now, you may have thought, wait, hold on. Why this way? Couldn't you also have done something slightly different? For instance, couldn't I have also marked it instead as put x, y, z, like that? Is that not also a way we could have done things? And the answer is yes, these both work. But you'll see that we consistently go here. You might say, well, is there a reason for that? Well, essentially what we've done is we've chosen an orientation for our space. And orientation is actually a really big deal in calculus. And oftentimes orientation comes down to plus versus minus. And we go with this orientation, and this one right here, this is your right hand orientation. And so you might say, oh, wait a second, I seem to recall something about a right hand rule. Yes, and so that's why if we put this in this manner, it's consistent with the right hand rule. So that's why we'll label things in this way. All right, and so then you might say, well, so is this the left hand orientation? Yes. Is this wrong? No, it's just a choice we make. But I just want to point out there is a choice we make, and there's a reason we make a choice when we do it. All right, so we have a central point, the origin, and we have directions which we can move. And with that, we can describe any location in 3-dimensional space. The way we do it is we describe how much we've moved in each direction. So let's pick a point here. And now here's our point. Well, I'm going to drop down here and go across and go here. So if you think about what's happened, and my picture is going to get really crowded if I don't be careful here. So I'm going to fill in the rest of this box. And if you're wondering, like, what does this box represent? So here's our point. So here's our x, y, z. So this is how much I've moved in the x direction. So that's this length here. This is your x change. How much you move in the y direction. There's your y change. And how much you move in the z direction. That's your z change. X, y, z. Now that we have that, we say, okay, well, great. I can describe, again, any point by moving in those directions by those prescribed amounts. Okay, well, what are some things we'd like to know about this space, or what are some very important features of this space? We should talk about the axes. So these are the axes. So let's talk about the axes first. We've already mentioned the origin. That's back here. The x-axis, what do we have? Well, in the x-axis, we only move in the x direction. There's no move in the y or z direction. So this point here would correspond to x, 0, 0. The y-axis, we only move in the y direction. There's no movement in the x or z direction. So this point here would be 0, y, 0. And similar for the z-axis. So the z-axis, we only move in the z direction, 0, 0, z. And by the way, the reason I drew this box is I said, oh, move x and y, then z. But you could also have said, oh, move z, and then move y, then move x. So any way to get from one corner to the other corner. All right. Now, we have our point, we have our origin, we have our axes, but there's also some other important features that we want to point out. Say, okay, let's look at, let me grab an appropriate color here. We'll go with this color again. Down here, what does this correspond with? Well, we moved in the x and the y, but not in the z. So this looks like x, y, 0. And we can look at all such points, and what we get is we get essentially, we can think of it as like the floor. And I do like to think of it in terms, let's think about it as though we were standing in a room. And z is going up and down, and x and y are directions along two of our floors. And so when we see this, what do we have? We say, aha, this is the xy plane. All right, well, great. We know how to describe that. And we say, okay, but we can do that with our walls, right? So let's say we come over to here. We say, all right, there's this wall. What do we have going on here? Well, over here, what are we moving? We can move in the x and the z direction. And so points look like x, 0, z. So this would be the xz plane. And, well, okay, we also have our back and wall. So we can mark that as well. And what's happening there? Okay, no surprise. We're moving just in the y and the z direction. And so this looks like 0, y, z. And this is the yz plane. Now, one nice thing is if I'm at a point and I want to say, all right, what's the nearest point to, say, an axis or to a plane, one of these xy, xz, or yz planes, I can actually find it very simply. So if I'm at xyz and I want to find the distance to the xy plane, I drop down to the xy plane. So in other words, xyz should be xy0. This point is the nearest to that point. Now, is there some intuition for that? Well, yes, there actually is, and we could go through and do a lot of algebra, but we can also just say, hey, you know what? There's a right angle here. And you'll see that it's very normal. Oh, that was a good pun. You may not realize it, but that was a great pun. It's very normal to see that when we want to minimize distances, we should get right angles. And so it's that perpendicularness that helps us. Now you might say, okay, well, what if I wanted to get the nearest point on the x-axis? Well, no problem. What we do is we say, look, on the x-axis, I need y and z terms to be 0, and then x can be anything I want. So if I want them to be as close as I can get, you say, all right, go straight across the face of this box, and you'll get x0, 0. So the closest point on the x-axis to xyz is x0, 0. And similar for the y and z axis. Now we talked about close. And if we're talking about close, we have to talk about distance. So let's do a quick discussion about distance. All right, so how do we find how far apart things are? Well, we have ways to do that in 2 dimensions. And so let's do a quick recap. So in 2 dimensions, suppose I have a point, I'll call it x1, y1, and then way over here, I have another point called x2, y2. And I'm interested in the distance between them. So in other words, imagine drawing a straight line, and you pull out a ruler. What's the length of that line segment? A fancy word you may occasionally encounter will be geodesic, and geodesic is just a fancy way of saying shortest distance. Okay, so we know we're looking for the shortest distance here. Well, we say, we have tools. And one of our favorite tools in math is something called the Pythagorean theorem. And the way it works is you say, well, draw a triangle. But not just any triangle, choose the right triangle. Because when you have a right triangle, the length of this side squared and the length of that side squared is the length of that side squared. So if we could find these two lengths, then life is good. Now the good news is these lengths are easy to spot. So this length, well, is really, it's a change in x. It's x2 minus x1. Okay, well, is it? That's a good question. We'll come back to that in a second. This length here, change in y. y2 minus y1. Okay, so now you might say, well, wait, why did you say is it? Well, you have to keep in mind that change can actually have an orientation. So you can say, oh, I'm going up or I'm going down. And so when we talk about change, we really should throw in some absolute values. So that's really the length of the slice, is the absolute value of these changes. Now, we throw in Pythagorean theorem. And the great thing is, if you square an absolute value, it's like squaring the inside. So we end up with that the hypotenuse squared is the change in x squared plus the change in y squared. Ah, wonderful. So then if I want the distance, all right, take the square root. All right, x2 minus x1 squared, y2 minus y1 squared. Okay, and that's for 2D. Well, what about 3D? What can we do? What can we do? Well, the answer is we can do something fairly similar. Now you might say, well, wait, I don't remember learning the Pythagorean theorem in 3 dimensions. Well, you don't have to. You can bootstrap. And so we're going to form a little box here. So let's suppose this is our first point we have, and the other point is the opposite corner, okay? All right, so again, we have our points. We'll say that this point over here, this is our x1, y1, z1, and this opposite corner is our x2, y2, z2. Now, we would strongly like the distance to be very similar. Okay, well, in other words, we say, hey, we draw this line, we're after the distance between those two. And now we just say, look, build your way up there a little bit at a time. So we can say, here's our x direction, here's our y direction, right? Because we have this underlying x, y, z. So we have our change in x over here and our change in y over here. And notice, I could just take this straight line across. We'll call it E for a second. And we say, these are perpendicular because we've made these directions perpendicular. So I have a right triangle here. So I can say that E squared is the change in x squared plus the change in y squared. All right. Now, say, okay, we know that length. We want that length. And lo and behold, these are at right angles. Why? Well, because the z direction is perpendicular to the xy plane. Because essentially this is the xy plane just moved up. And so this is coming up perpendicular. We say, oh, great. So this length here, that's our change in z. So we get that d squared is this length squared, e squared, plus change in z squared. But we know what e squared is. That's what we did up here. So our distance squared, again, change in x squared, plus change in y squared, plus change in z squared. Take the square root. Life is good. And you have your formula. All right. But we will rewrite it in the following way. Namely, it's the square root of x2 minus x1 squared, y2 minus y1 squared, and z2 minus z1 squared. Just like we would have thought. In fact, we probably would have guessed it if you said, hey, what do you think the formula should look like? I said, I would hope it would look something like this. And you'd be like, yeah. And it is. And it is. And spoiler alert, if we could draw 4 dimensions on a piece of paper in a reasonable way, we would see that the distance in 4 dimensions is very similar. We can keep going like this. Okay, let's do a problem. All right, so I have a problem prepared here. And you can see it was prepared because I actually printed it. And it says, find the distance. So we have the distance from the point 3 minus 4 root 7 to the following. The origin, the x-axis, y-axis, and z-axis, the xy plane, the xz plane, and the yz plane. All right, this is a great chance if you're following along at home. Pause. Take a moment, work it out. All right. Did you pause? Okay, so let's talk about what's going on. So we have our 3-dimensional space, and we can try to draw semi-accurately. We don't have to, but let's suppose we were actually trying to do it just for today. So we're moving 3 units in the x direction, -4 in the y, and root 7 in z. Okay, so that would put us somewhere over here. Now, I will say, accurate pictures are usually not too critical. What's more critical is intuition. So if you have to choose between accuracy versus intuition, go for the intuition. And then if you need the accuracy, you'll throw that in later. All right. Well, now, let's suppose we were to think of this as we were in a box. And so we're going to draw our box in. And yeah, I can draw straight lines occasionally. All right. Okay, so now we have to find the distance to various points. And we can do this in any order. And so we have the origin, the x-axis, the y-axis, the xy plane, the xz plane, and the yz plane. Okay, well, we actually have a few of them which are very quick, and that's the planes. The planes are very quick. Why? Because suppose I'm here. How do I find the distance to the xy plane? Well, I know how to get to the xy plane. Namely, I drop straight down. So the nearest point on the xy plane looks like 3, -4, 0. How much did I change? Well, I changed by the z coordinate. So this distance here is root 7 distance. Okay, so to the xy plane, root 7. Well, what if I wanted to say get into the xz plane? Okay, well, the nearest point on the xz plane is over here. What does it look like? Well, it looks like 3, 0, root 7. In other words, in the xz plane, the x and z can be non-zero, but the y part has to be 0. All right, what's that distance? Okay, careful. Now, you might say, it's -4, right? Because I see a -4. You can't fool me twice. Or I haven't fooled you at all yet. But what are we after? We're after distance. And so -4 is the change, how we moved, but it's not the distance that we moved. Because the negative, really what happens is negative indicates some sort of direction. And so positive would go off in this direction and negative would go off in that direction. And so negative is an orientation, it's a choice of direction. But distance is a measurement. And so when we talk about distance, it's going to be the positive amount traveled, if you like the absolute value. So we get 4. And finally for our yz plane, we're going back. And for the YZ plane, it would look like 0 minus 4 root 7. And so the distance we traveled is 3. Okay, so getting to the planes are pretty quick, actually. It's these entries. Now, what about the origin? Well, the origin is just the distance from this point to 0, 0, 0, right? Because that's where the origin's at. So I say, okay, well, I know how to find distance between a pair of points. We just wrote down the formula. So that's the square root of 3 squared, negative 4 squared, root 7 squared. Okay, 9, 16 makes 25, plus 7 makes 32, square root of 32. Could we simplify? Yeah, we could simplify. We could say it's 4 root 2. Do we need to simplify? No. What? I thought the high school teachers always said you have to simplify everything. Well, no. You have to simplify things when we ask you to, but square root of 32, lovely answer. As long as it's the correct answer, life is good. Now, I see that I forgot to write down one of our axes here. You're like, Steve, you forgot to write down one of your axes there. I know, I'm sorry about that. Let me write it down now, z-axis. So how do we find to the axes? Well, let's suppose I want to go to the x-axis. You go across the face here, and you say, what does the x-axis term look like? It looks like 3, 0, 0. So the change in x is nothing, and then you have the change in y is at negative 4, and the change in z is root 7. So it would be the square root of 0 squared plus negative 4 squared plus root 7 squared. And, okay, 0 plus 16 plus 23. And, 16 plus 7 is 23. I can say words. All right. And if I want to go to the y-axis, I'm going to cross this face down to here. And I'll get to the point, which is 3, 0. Y-axis 0, negative 4, 0. So only the x and the z matter. So this would be the square root of 3 squared, 0 squared, root 7 squared. 9 plus 0 plus 7, 16. Square root of 16, that one we can simplify. That's 4. And finally, the z-axis. And the z-axis, okay, 0, 0, root 7. And so is the square root of 3 squared, negative 4 squared, and then 0 squared. And square root of 9 plus 16, square root of 25, which is 5. Okay, and there we go. And so we can actually find distances pretty easy. This one is kind of about distance, but ultimately at the end of the day, what it's really about here is it's really about saying, how can I get from this point to the xy plane, xz plane, yz plane, and the x-axis, the y-axis, and the z-axis? It's understanding how to get those measurements. Understanding what do points represent. All right. So our last thing we're going to talk about today is going to be spheres. And so what is a sphere, and how do we describe them? So a sphere, well, it's a three-dimensional ball. And so we have this orb, if you will. Now there's two important characteristics for a sphere. There's a center and there's a distance, which we call the radius. So the center, we'll call this center point H, K, and L. And then we'll have a radius, which we'll call R. And so the sphere is the set of points distance R. So here's R from a center H, K, L. So you have a center and you have a radius. Now when we're talking about a sphere, keep in mind when we say the sphere, we really mean this sort of candy coating. It's like, you know, the M&M, like the candy coating. It's not the inside, it's not the outside, it's just the edge there. Now, how do we find it? Well, the good news is we have an expression here. We have a distance. We say, okay, all right. So we say, okay, suppose I have a point here, x, y, z, that's on my sphere. What must be true? Well, what must be true is that the distance between x, y, z and the center must be r. And we have a formula for distance. So I say, okay, so we have the square root of, you do the difference in the x entries, the difference in the y entries, and the difference in the z entries. And that has to be the radius. So that must be true. And now we say, well, we don't like square roots. I know, I don't like them either. So let's get rid of the square roots. And we can do that if we square both sides. And lo and behold, we get this is true. So if I'm a point on the sphere, I must satisfy this relationship. But if I satisfy this relationship, that means I'm distance r away from the center, so I must be a point on the sphere. So this is the formula. Say, all right, woohoo, we found the formula for a sphere. Nice, nice. This is wonderful, wonderful. All right, okay, well, that wasn't so hard. Ultimately, sphere comes about by saying, let's look at distance. Now, quick side note, I mentioned that this is our candy coating. What if I wanted the inside of the sphere, say up to and including the boundary? Well, then would say I want the distance to be what? At most r, like less than or equal to r. So the inside of the sphere would be less than or equal to r squared. So this is our interior, and including our boundary. And what if I wanted the outside? Well, the outside would be what? If we were greater than or equal to r squared. Oops, that's our exterior. And so that's just a side note. Okay, well, now, one thing we should pause and say, hey, remember when? What's going to be an important thing for us to be able to do to talk about spheres? Well, we need to talk about completing the square. And flashback, right? We talked about our illusion of knowledge. We've got to remember our basics. Why do we need to talk about completing the square? Well, because we have lots of square terms. And suppose we had something like this. X squared plus 2x plus y squared plus 4y plus z squared minus 8z equals 21. Okay, I claim this is a sphere. And I say, well, where's the center of the sphere? What's the radius of it? And you're like, what's our problem? Well, it's not quite in this form. Now, why do I claim it's a sphere? Well, essentially, there's a dead giveaway. You say, oh, I see x squared plus y squared plus z squared. And when we see x squared plus y squared plus z squared, we're like, oh, yeah. It's very spherish, very, very spherish of us. We say, okay, well, what will we do? We'll make it look like that. How do we get there? Well, we say, okay, we want to complete the squares. So we want to make, x squared plus 2x, we want to make it look like a square. And so we're going to give ourselves, here, we'll rewrite this, x squared plus 2x and plus something. We'll have a suspicious gap. Y squared plus y plus something. And z squared minus 8z plus something equals 21. And so the idea is, you say, to complete the squares, what would you want to add here so that this was a square? Now, what's the idea? Well, the idea is surprisingly simple. And at least I think so. And I think most math ideas are very simple. It's actually carrying out. The details might get us bogged down. But you say, okay, I have x plus something squared. Well, that's a square, so it would be x squared plus, when you multiply this out, it would be 2 something x plus something squared. So if I say, okay, I have x squared plus something in the middle, what do I need to add? Well, what do? The rule is you say, okay, look in the middle term. So see how you have that 2 times something? So you say, oh, well, that's 2 times the thing I need. And so you divide it by 2 and like, aha, good news, I have the thing that I need. And now you say, well, now that I know what I need to square it and add it on. Okay, so let's go through and do this. 2, well, divide that by 2 is 1. Square 1, we need to add 1. But wait a second, we've changed it now. You can't just arbitrarily put things where they're convenient. Well, no, that would be wrong. So what do we need to do? Well, we need to balance it, right? So you're allowed to modify equations as long as the net change of your modification is 0. Or I should say, as long as your net change is no effect. So one thing you can do is you can say, well, I can add 0 or multiply by 1. Those are 2 things that we do a lot. So adding by 0 just means make sure you do something so that the effect balances out. So if I add 1 here, one thing I can do to balance it out is I add 1 there. Okay, next term, y squared plus 4y. Middle term, I see the 4, take the 4, divide by 2. That's, well, 2. 2 squared is 4. Great. So add 4. Again, balance it out. Z squared minus 8z. Okay, take negative 8. That's what's attached to the z in the middle. Divide by 2 is negative 4. Square negative 4, is it 16? Or is it negative 16? It's 16, positive 16. Yeah. Square negative, you get a positive. Again, balance it out. Okay, so doing this, we say, life is good, because now that's a perfect square. Oh, that's a perfect square. And oh, wow, that's a perfect square. Almost like we planned it. Well, because we did. Now, what about this side? Well, we add the numbers together. 16 plus 4 is 20 plus 1 is 21 plus another 21 is 42. Some people think that's the answer to life, the universe, and everything. But for now, it's 42. Okay, so that's why we need completing the square, because we need to figure out how to get it into this form. Now, where's our center and what's our radius? And here is a place where we again can make a few mistakes. Is our radius 42? No. Why not? Because that's r squared, right? That's radius squared. So the radius is the square root of that side. Great. Now, what about our center? It's so tempting to say, oh, it's 1, 2, negative 4. But is that right? No. See how we have x minus h, y minus k, z minus l? We're subtracting things. So secretly, even though it says x plus 1, we should think of it as x minus minus 1. And similarly, y minus minus 2. And z minus 4. Oh, well, okay, that didn't have to do anything. Z minus 4. So our center is negative 1, negative 2, positive 4. All right, so there we go. There's our sphere. All right, so to finish up, we are going to do a quick multiple choice. We got to get used to doing this because particularly for this particular run of the class this semester, we're going to have multiple choice problems on the exams. And so we need to learn how to do them. Okay, so for which value of A does the following equation correspond to a sphere of radius 4? X squared plus 4x plus y squared plus z squared minus 6z equals A. All right, so we have some choices. A equals 3, A equals 4, A equals 9, A equals 16, A equals 21. Now, let's put on our hats here. And in fact, this is a great chance for you to pause, work it out, and then come back. Okay, so I'm going to give you a chance to pause. All right, are you back? Great. So I want to point out, we know how students think. And the reason we know how students think is because we programmed them. We taught you how to think. And so we also know common mistakes. Now, if we hadn't just talked about things, what would be a common mistake? Someone would say, put the radius here, 4. So that's why we have an answer of 4. Or, no, it's not the radius. Haha, you silly goose. It's the radius squared. Put 16. Oh, we've made 16 an option. So we put in things which are very tempting. In other words, we put in things that look like they could be the answer. Be careful. Don't be misled. All right. So what do we do? Well, we say, look, we really want to have this side. What happens after we complete the square, right? So we say, okay, so x squared plus 4x. And then what would we need to do to complete the square there? Well, okay, 4 divided by 2 squared. Now, we need to add 4. The y squared, well, there's no need to do anything. By the way, one thing I forgot to mention is when we do have like x squared terms and x terms, we like to combine. X's like to hang out with the x's, y's with the y's, and z's with the z's. So if they aren't already there, put them there. Z squared minus 6z, what do we need to add? Well, negative 6 divided by 2 is negative 3, and negative 3 squared is plus 9. Now, we'll put a plus 9, and that equals a, but of course, because we're balancing out, plus 4 plus 9. And, all right, well, great. And now we say, okay, this is whatever it is. We're just after a radius of 4. So this side, we need to have this be equal to what? 16, 4 squared. And we say, oh, okay, so we get a plus 13 needs to equal 16, so a better be 3. And there you go. So there's our answer, a equals 3. Another thing, that answer that we throw in there, just to be very tempting, is negative 6. Maybe you said, oh, I should subtract 9. And if you subtracted 9, you would have thought it was 21. So again, be careful. Be careful. I don't want you to overthink things, but don't just say, it's obvious here. I'll check. I got an answer. It must be right. No, we're really good at putting in bad answers. Okay. Well, thank you for being patient and going through this video. Again, I apologize that we weren't able to record it in class. The following ones will be recorded in class. Whether that's better or worse, we'll find out. But I hope you come again. All right. Take care. Bye.